I'll start with a single electron. Not a crowd of particles, not a storm of mathematics, just one electron, set free in a darkened laboratory. I prepare it carefully. So carefully that I can release one at a time toward a thin barrier cut with two narrow slits. On the wall behind the barrier sits a screen, waiting. The electron flies, the laboratory holds its breath, and there a single bright dot appears, then another, and another. I keep going, one electron at a time, each leaving only a solitary dot. Hours pass. Eventually, if you stand back from the screen, an airy zebra pattern of bright and dark bands emerges. Waves make patterns like this, but I didn't send waves, I sent individual particles. That quiet contradiction is the doorway into quantum physics. What the pattern tells me is simple and astonishing. An electron is described not by a tiny billiard ball tracing a single pre-written route, but by a quantum state, a wave of possibility that can explore many paths at once. When I refuse to ask which slit the electron took, I see the full grace of that wave in the interference pattern. When I insist, when I place a detector to discover which way, the pattern collapses into something ordinary. In quantum mechanics, the question you choose to ask helps to decide the answer the world can give. That is not mysticism, it is how nature behaves when you coax it to reveal its grammar, one particle at a time. So what precisely is doing the waving? Not a ripple of stuff, but a ripple of information. We call it the wave function. It evolves smoothly and deterministically, guided by Schrödinger's equation, until something like a measurement couples the system to its surroundings. Then the delicate superposition of possibilities gives way to one actual outcome on your screen. People often say the wave function collapses, but you can think of it more physically as information leaking into the environment. Photons, air molecules, the atoms in your detector, all of them carry away small records of what has happened. Quantum possibility decoheres into classical fact. At first glance, this seems to offend common sense. But common sense is an evolved survival tool. It is tuned for throwing stones and brewing tea, not for understanding electrons. The miracle is that quantum mechanics, for all its strangeness, is a triumph of common methodology. We write down a compact mathematical statement of how the world behaves, we deduce consequences, and we compare them with experiment. Time and again, the experiments side with the quantum story. That reliability should comfort you. We are not trading clarity for dreams, we are replacing an inadequate picture with one that works. There's a second, quieter revelation hidden in the double-slit story. The solidity of everyday life is not a separate kingdom walled off from the quantum realm. It is born from it. Tables are firm because electrons are fermions and obey the Pauli exclusion principle. They refuse to share the same quantum state. That polite refusal is why matter resists being squeezed into the same place. The ground you walk on, the page you turn, the breath you take, all are quantum rules writ large. Decoherence does the rest. In a warm, bright world, superpositions leak information so quickly that you almost never witness interference beyond the laboratory. The classical calm is not a denial of quantum mechanics, it is its consequence. When I teach this, I try to resist the temptation to reach too quickly for slogans wave and particle, or measurement creates reality. Slogans are postcards from countries you ought to visit in person. Better to linger with the experiment. Let one electron after another arrive. Watch the pattern grow from dots to bands, from chance to law. Feel the cadence of the statistics. The quantum world is not chaotic noise. It is order with a new accent. You ask a question, where? With what? Momentum. Through which slit? And the theory gives you a distribution of answers. Then you perform the ritual of repetition, and the frequencies converge with exquisite regularity. The probabilities were not excuses. They were predictions. If that sounds unsettling, it is also liberating. It means we live in a universe that is playful, yet precise. You and I are free to design the questions, to engineer devices that draw out particular aspects of a system's quantum character, and nature meets us exactly on those terms. You are not a passive observer. You are part of the interaction, and the interaction matters. Measurement in this view is less about pulling back a curtain and more about stepping onto a stage. When you step on, the play changes, but always according to a script you can learn. This is why I prefer to describe quantum mechanics as humble rather than paradoxical. It does not claim to unmask the inner essence of reality in a single stroke. It offers a compact algorithm for expectation. Yet from that algorithm flow the colors of neon, the structure of atoms, the reason the sun shines. From it come lasers and transistors, atomic clocks and MRI scanners. And in the past few decades, a more audacious frontier has opened. Quantum technologies that exploit superposition and, especially, entanglement. They are not magic tricks. They are engineering projects that take the grammar of the microscopic world seriously. Before we turn to entanglement, let me tidy the picture we've painted. A quantum state is a book of possibilities. Preparation writes the first chapters, evolution turns the pages at a steady rate, and measurement chooses one line to read aloud. If that line offends your classical intuition, if you wanted the electron to carry a tidy passport stamped left slit or right slit, remember that intuition is a habit, not a law. The electron is honest. It tells you through the pattern on your screen exactly the world it inhabits. You asked it to speak in the language of waves, and it did. Now lift your eyes from the laboratory wall for a moment. The same mathematics that lets a single electron be many paths at once also allows many particles to share a single description. That shared description entanglement is not mere correlation. It is a union so deep that the whole contains information. The parts, by themselves, do not. Einstein called it spooky, and for good reason. It stretches our idea of locality without breaking causality. It refines what we mean by separate. In the next part, I'll step carefully onto that stage and show how two far-flung systems can behave as one, why this does not allow faster-than-light signaling, and how the same phenomenon underwrites quantum communication, sensing, and the first tentative stabs at quantum computation. For now, keep the image of the screen in your mind. Single dots, patiently accumulating into something that looks like intention. That is the rhythm of quantum theory, quiet, faithful, and, once you've seen it properly, irresistibly beautiful. Let me turn to the strangest sentence the universe has ever taught us to read: entanglement. I prepare two tiny systems, say a pair of electrons, so that their spins are born correlated. Not classically correlated like two coins secretly fixed to show heads, but bound together in a single quantum description. I fly one electron to the far side of the lab and carry the other to my desk. When I choose how to measure mine this way or that, the statistics of the result over many trials are linked to the statistics of yours, even if you're across the corridor, across the city, or halfway around the world. It was this that led Einstein to grumble about spooky action at a distance, and Schrödinger to say entanglement is the essential quantum trait. Those are not just barbed phrases, they frame a genuine puzzle that sat unresolved until the late 20th century, and, in a sense, culminated in the 2022 Nobel Prize in Physics. The puzzle is this: could the correlations be explained by hidden properties, little instruction cards each particle carries from the source, so that no influence travels between them? In 1964, John Bell found a way to turn that philosophical worry into numbers. He derived inequalities that any theory with local hidden variables must satisfy. Then experimentalists, first in pioneering form by John Clauser, and later with exquisite care by Alan Aspect and Anton Zeilinger, put nature on the stand. The verdict was unambiguous. The quantum correlations violate Bell's inequalities. The world is not secretly classical beneath the surface. Whatever picture you keep in your head must make room for entanglement's non-local correlations. That's what the 2022 Nobel recognized: decisive, loophole-closing experiments, showing that quantum mechanics really does outpace any local hidden variable account. That sounds like faster-than-light magic, but here the universe is both subtle and kind. Entanglement strengthens correlations, yet it refuses to be a telegraph. The no communication or no signaling theorem tells us why. However you twiddle your apparatus on your side, you cannot use those entangled correlations to send a message to me instantaneously, because my local outcomes look completely random until we later compare notes. Entanglement is a conspiracy of statistics, not a phone line through the void. That is why quantum theory remains at peace with special relativity, even as it disrupts our older intuitions about separateness. Every time I describe this, I pause with the pair of electrons in my mind and listen for the cadence underneath the mathematics. We prepared one state for the two together. That is the crucial shift. Classical thinking invites us to assign each particle its own private dossier. Quantum mechanics says, read the joint file first. It's a relational theory at heart. Many of the most interesting things it tells you are statements about wholes that cannot be reduced to parts. That is why entanglement isn't mere correlation. You can have strong classical correlations without violating a Bell inequality. What makes the quantum version special is that the whole contains information the parts do not and cannot possess on their own. Very well, you might say, then how do we square this with the solid world? The same way we did before, decoherence. Entanglement is promiscuous. The delicate two-particle state you cherish will, in warm daylight, become entangled with trillions of degrees of freedom air molecules, scattered photons, the atoms in your apparatus, and the fine interference structure you rely on is washed out into classical-looking behavior. The environment measures you all the time, selecting robust, effectively classical pointer states that survive the buffeting. That's why tables stay tables and cats don't stroll about as superposed rumors. Decoherence doesn't solve every interpretational riddle, but as a physical mechanism, it is one of the great clarifiers of the last half-century. If you want a more technical tour, look to Zurek's and Schlosshauer's reviews. They lay out how environmental entanglement singles out stable states and suppresses interference in practice. This interplay entanglement at the foundation, decoherence at the surface, does more than soothe philosophy. It powers technology. Quantum key distribution leans on the impossibility of copying or peeking at quantum information without leaving a trace. Quantum sensors exploit fragile superpositions to measure fields and time with absurd precision. And quantum computation attempts to choreograph entanglement across many qubits to do work that classical bits would find intractable. When I speak about this in public, I stress that there's no mysticism hiding in the circuitry. It's engineering, built atop the same principles we teach first-year students. State preparation, unitary evolution, measurement, and the stubborn constraints those words imply. For a compact modern overview in my own words, my recent Quantum in 22 Minutes piece sketches the ladder from foundations to applications. It helps to keep a simple model in your head. Imagine two spin, half particles in the singlet state, a perfect antipair. If I choose to measure along one axis, and you choose another, the joint statistics will violate a Bell inequality in exactly the patterns experiments see. We're not trading in vague metaphors here. The numbers match what Aspect and colleagues extracted from photons, what Clauser first brought into a laboratory setting, and what later teams improved with loophole-free designs. When the Nobel press release summarized that this rules out local hidden variables. It was distilling decades of increasingly careful work. The physics classroom and the prize dais are, for once, in complete agreement. If entanglement cannot signal, what is it good for? Think of it as a resource for coordination. You and I can share an entangled state, perform agreed-upon local operations, and later compare classical notes to accomplish tasks impossible with classical correlations alone. In quantum teleportation, for example, we use pre-shared entanglement and a 2-bit classical message to reconstruct an unknown quantum state at a distance without moving the physical carrier. Nothing gets there faster than light. The protocol waits politely for those classical bits. But the trick would be unworkable without entanglement's peculiar glue. The popular material around the Nobel is again a friendly gateway if you want the intuition rather than the circuit diagrams. What I love about all this is how it changes the emotional register of physics. Classical mechanics sang about certainty and isolation. Objects had properties, and those properties evolved. Quantum mechanics sings about possibility and relation. Systems have joint descriptions, and what you can say about the parts depends on how you ask about the whole. Once you accept that shift, the rest follows with a disarming, almost musical consistency. You prepare, you evolve, you interact, you record, and through it all, the theory keeps time. In the next part, I'll keep that rhythm, but change the key. We'll move from the conceptual scaffold superposition, entanglement, decoherence, into the nuts and bolts of quantum information, qubits instead of bits, interference as computation, error correction as the art of protecting delicate states from a noisy world. I'll try to keep the language slow and the steps small, because the ideas settle better that way, like ripples fading on a pond until you can see the moon reflected cleanly again. When I say that entanglement changes the emotional register of physics, I'm not being poetic for its own sake. It quite literally changes the way we build. If classical computing is an orchestra of on-off switches, then quantum information is an ensemble that can hold harmony, superpose notes, and keep time across distance through entanglement. The elemental unit of that harmony is the qubit. A qubit is not a tiny coin that's either heads or tails. It's a prepared quantum state that can be in a superposition of 0 and 1, with the relative phase between those possibilities, doing real computational work when we let states interfere. That's the heart of the idea. And if you want a concise definition stripped of metaphor, the industry primers say it exactly like that. To feel what a qubit is, I imagine the double slit again, then shrink it until it lives on a chip. I prepare a 2-level quantum system, an electron spin, or the ground and excited states of a superconducting circuit, and I shelter it from the world so it can keep its delicate phase relationships intact. I can rotate it gently on a Bloch sphere, letting it sweep from north root to south root through every point in between. Those rotations are my single qubit gates. Let 2 such systems interact, and I can weave entanglement my 2 qubit gates. Out of that small grammar, prepare, rotate, entangle, measure, an entire computational language emerges. It sounds like sorcery until you've watched the interference patterns add and cancel just as they did on the laboratory wall. Except now, the screen is an algorithm's answer. This is where people often ask, so, is a quantum computer just trying all answers at once? That's a tempting story, but it isn't quite right. The art is subtler. We choreograph interference so that paths that correspond to wrong answers cancel, while paths that lead to right answers reinforce. The computation is in the pattern of reinforcement. That's why the phase, the invisible angle between the 0 and 1 parts of a qubit, matters so profoundly. It's the knob we tune so that probability flows, like water in a carefully cut channel, toward the answers we seek. If you'd like a brisk tour of this ladder, from superposition to algorithm, I've sketched it in a recent 22-minute primer. Superposition, interference, entanglement, then applications. Of course, nature does not give us perfect instruments. Qubits are noisy. They forget. Left alone, they shed their energy with a characteristic T1 time, and their phase coherence blurs with a characteristic T2 time. The environment is a gossip. It leaks information about the qubit's state into every nearby degree of freedom. And once that gossip spreads, the pattern you wanted to build dissolves. The answer is not to wish the noise away, but to correct it. Quantum error correction sounds paradoxical at first. How can I copy a fragile quantum state when the no-cloning theorem forbids copying? Until you learn the trick. We don't copy, we spread the information across many physical qubits so that no single qubit carries the whole state. Then we measure complementary syndromes that reveal which errors occurred without ever peeking at the encoded quantum information itself. With enough redundancy and careful design, surface codes are the current workhorse. You can keep logical qubits alive far longer than any of their constituents. That's not marketing. It's a mathematical and engineering framework that's been surveyed clearly in modern introductions. There's a beautiful theorem behind the engineer's optimism. If you can keep your physical error rates below a certain threshold, and you have enough qubits to devote to protection, then fault-tolerant quantum computation becomes possible in principle. The exact number depends on the code and architecture, but the message is robust. There exists a non-zero error rate beneath which scaling up reduces errors faster than they accumulate. That's the threshold theorem, and you'll find versions of it in accessible material from standards bodies and long-view surveys. It moves the problem from metaphysics to engineering, lower the error per gate, increase the code distance, and protect the algorithm. What does any of that feel like in hardware? In my mind's eye, I walk through 3 rooms. In the first, a dilution refrigerator hums softly, superconducting qubits patterned on chips, controlled by microwaves, read out by resonators. In the second, a string of trapped ions floats above a gold electrode chip, nudged by lasers to dance entangling gates with slow elegance and high fidelity. In the third, photons stream through interferometers on photonic chips, their polarizations or time bins carrying qubits immune to many forms of noise, ideal messengers for quantum communication. Each platform has a different temperament. Each writes the same grammar with a different hand. Popular explainers do a tidy job of comparing them without overselling any single approach. Roadmaps too have shifted in tone. A few years ago, everyone brandished raw qubit counts. Now the conversation has matured into logical qubits, error-protected units that can run deep circuits and the infrastructure to keep them supplied. Companies publish targets and dates. They talk about surface code distances, cryo-CMOS control, multiplex readout, and chip-to-chip links. You should treat dates as aspirations, but the direction of travel is clear. Build toward hundreds of logical qubits first, then thousands, and only then talk about algorithms that outrun what classical machines can do. Recent reporting lays out that pivot crisply. Timelines tied to achieving around 200 logical qubits, and hardware designed around error correction economics rather than just headline numbers. Even so, I keep returning to first principles when I try to explain why it matters. A qubit is useful not because it is exotic, but because it is honest about how nature computes. When I prepare a superposition, I'm not invoking magic. I'm aligning with the way electrons and photons have always behaved. When I weave entanglement, I'm not breaking locality. I'm writing a joint description on the universe itself prefers. When I protect information with a code, I'm not cheating around the no-cloning theorem. I'm respecting it and working within the rules to keep phase relationships intact long enough to be useful. And what counts as useful? Here, caution and excitement walk hand in hand. The mature algorithms that promise clear advantages factoring, certain quantum simulations, specific optimization and sampling tasks, are hungry. They want fault-tolerant machines. But there is an intermediate frontier quantum simulation of small, strongly correlated systems. Improved sensing, secure communication where today's devices and near-term, error-mitigated methods can already do science. In other words, while the grand vision waits for logical depth, the present is a laboratory, and we're learning how to speak the language of phase and interference fluently enough to ask sharper questions of nature. For an approachable on-ramp to that philosophy, start small, get the grammar right, see the short Quantum in Minutes session I mentioned earlier. If you strip away the jargon, what remains is a simple cadence. Prepare cleanly, evolve coherently, entangle deliberately, measure gently, and repeat until the statistics sing. That's as true for 1 qubit under a refrigerator bell jar as it is for 1,000 logical qubits solving chemistry at scale. It's also why quantum information sits so comfortably next to the foundations we began with. Superposition, interference, entanglement, decoherence. None of these are separate chapters, they're verses in the same song. And if you listen closely, you'll notice that even the practical roadmaps, full of dates and devices, are really attempts to keep that song in tune against a noisy world. In the next part, I'll let that song carry us into specific examples, how interference becomes an algorithmic lever, how error correction is actually performed on a surface code, and why logical qubits are the unit that matters when we talk about useful quantum machines. For now, let the picture settle. A handful of qubits held steady in the cold, phases aligned like the hands of a clock, and a computation that is less about brute force and more about letting the right notes resonate. I promise to make interference feel like an algorithmic lever, not a poster on the wall. So, I picture a register of qubits laid out before me, each one a tiny compass needle that I can tip and turn with microwave pulses or flashes of light. My first move is almost always the same: create superposition. Spread amplitude evenly across many computational paths, as though I'd opened all the doors in a hallway at once. Then I begin to choreograph phase rotate, those little compass needles, so that paths encoding wrong answers cancel, and the paths encoding right answers reinforce. That's the essence of amplitude amplification, the general engine behind Grover's search, a quadratic speed-up in the number of oracle calls, because interference is doing directed work rather than blind enumeration. It's less try everything at once and more tune the phases so probability flows where you want it. Grover's algorithm is the canonical case. Amplitude amplification is the broader idea that contains it. There is another tool that once seen you can't unsee: phase estimation. You give the machine a unitary process, do this transformation, and an eigenstate of that process, and ask for the phase, the tiny angle that tells you how the state picks up a twist when the unitary acts. With clever use of interference and a handful of control registers, the algorithm reads that phase with exquisite precision. It sounds abstract until you realize how often the question, "What's the phase?" is exactly the question a scientist needs to ask. Chemistry, materials, even certain optimization tricks all become tractable when you can estimate phases efficiently. And phase estimation reappears inside other famous algorithms. It's a subroutine, a quiet backbone. If you want a compact walkthrough, what the circuit looks like, why the precision scales, as it does the standard explainers, lay it out clearly. But algorithms, like instruments, are only as good as their tuning. In the quantum world, the tuning is error correction. Left to themselves, qubits lose energy, and worse for computation, they lose phase, those delicate angles you and I just used to herd probability. The cure is not to copy a qubit, nature forbids that, but to spread its information across many qubits in such a way that small, local blunders can be detected and reversed without ever peeking at the logical state itself. That's the stabilizer. Idea introduced in the 1990s. You define a quiet subspace, the code space, by a set of commuting checks. You repeatedly measure those checks with ancilla qubits, and the pattern of plus or minus one outcomes, the syndrome, tells you which error lightly struck. You mend the fault while keeping the encoded quantum information hidden from view, intact and private. This is the stabilizer formalism in a nutshell. The syndrome extraction picture in Accessible Reviews is particularly good for building intuition. From that language grows the surface code, a pragmatic favorite, because it only asks qubits to talk to their nearest neighbors on a 2D grid, and yet tolerates impressively high physical error rates. You tile the plane with data qubits and interleaved ancillas, measure X-type and Z-type parity checks every cycle, and decode the stream of little plus or minus one flags into an evolving picture of where errors must have landed. Increase the code distance d, the linear size of a patch, and the logical error rate falls roughly exponentially, provided your hardware sits below a threshold. Numbers matter here. Experiments over the last few years have shown precisely the behavior error correcting theory, promised logical errors shrinking as the distance grows, and have begun to operate in the regime where the logical qubit is, in a meaningful sense, more reliable than any of its constituents. For the conceptual and historical background, see Fowler et al. For experiments demonstrating suppression by scaling and below threshold operation. See recent Nature results. Logical qubit is the operative phrase. A logical qubit is not a single device, but an encoded degree of freedom living across a whole patch of hardware. You don't so much build it as cultivate it. Keep the parity checks ticking, keep the decoder listening, and act only through operations that respect the code's stabilizers. You can visualize a distance d surface code, logical as living on a d times d square of physical qubits, with its own logical x and z operators spread like fault lines across the patch. Stretch the patch, raise d to make it tougher. Link patches to perform entangling gates. In that picture, progress in the field is increasingly measured not by raw device counts, but by the number and quality of logical qubits you can field at once. Nature's overview of surface code logicals makes this concrete. Even industry summaries now define logicals in terms of patch size and code distance rather than marketing qubit totals. The engineer's promise is formalized in the threshold theorem. If every little operation initialization gate measurement fails with probability below a certain value, then by adding enough redundancy, you can drive the logical error to as low as you like. The exact threshold depends on the code and the noise, but the existence of a non-zero threshold moves us out of metaphysics and squarely into engineering. Lower your error per operation, increase your code distance. Let the decoding do its quiet, relentless work. General references on quantum error correction and threshold behavior are standard now, and readable even outside specialist circles. What does this feel like in practice? I think of rhythmic, almost musical cycles. Measure all the parity checks, update your belief about where errors might be, apply tiny targeted corrections and move on to the next cycle. Logical operations like a C, not between two encoded qubits, are not single flicks of a switch, but braided procedures that thread through many cycles without disturbing the code's quiet subspace. You can even move a logical qubit across the chip by deforming its patch, or split and rejoin patches to create fresh entanglement, all while the decoder hums in the background. The operational picture stabilizer checks, syndrome streams, and logical operators defined across the patch is set out cleanly in both foundational and modern expositions. Now marry the two strands, algorithms and protection. A toy but telling example is to run a few rounds of Grover-style amplification on small encoded registers and watch the logical success probability rise as you increase code distance. Or perform a miniature phase estimation circuit where the only way to retain the promised precision is to keep the logical phase coherent across many cycles. Again, enlarge the patch and the logical dephasing falls. These are not marketing stunts. They are the day-to-day tests that show whether your machine can keep the quantum grammar alive long enough for interference to do useful work. For algorithmic baselines and why amplification and phase estimation are the standard levers, see the core references. If you've heard me in recent interviews, you'll know I try to keep the tone level. Excitement tempered by the honesty of error bars. The roadmaps have matured. We talk now about getting a few hundred high-quality logical qubits before we dare the really deep circuits that chemistry and cryptography demand. In the meantime, there is a world of science available to smaller devices. Simulation of tightly correlated quantum fragments, exquisitely sensitive metrology, secure links that lean on the impossibility of undetected eavesdropping. The heartening thing is that none of this requires a leap of faith. It asks only that we respect the rules we began with: superposition, interference, entanglement, prepare cleanly, evolve coherently, measure gently, and above all, guard the phase. For a sense of how I frame this ladder from foundations to applications in public talks, see the 22-minute primer. In the next part, I'll stay with the practical thread and walk through a surface code cycle, beat by beat, what the stabilizers are, how syndromes propagate, how a single stray click becomes a pair of detection events in the decoder's graph, and then I'll sketch how logical gates are actually performed without tearing the code. It's not sorcery, it's choreography, and once you hear the rhythm, you can't help but tap your foot to it. I want to slow the picture down until you can hear the machinery of protection at work one round of a surface code cycle, beat by beat. Imagine a flat grid of qubits. Some are data qubits that hold the fragile quantum information. Interleaved among them are ancilla qubits that do nothing but ask gentle, repetitive questions of their neighbors. Those questions are parity checks. One family asks about X-type parity, the other about Z-type parity, and together they define a stabilizer code on the two-dimensional lattice. That is the surface code, in essence. A choreography of local checks that collectively guard a global encoded state. A round begins by preparing the ancillas in simple states ket0 for Z checks, ket plus for X checks. Each ancilla then performs a short dance of controlled operations with its 4 nearby data qubits. The order matters, the phases matter, but the headline is simple. Information about whether an even or odd number of neighboring qubits have flipped leaks into the ancilla. We then measure the ancilla and reset it, ready for the next beat. Repeat that rhythm, prepare, entangle locally, measure, reset, and you obtain a moving picture of the code's health without ever prying into the logical information itself. What you collect from those ancillas are syndromes, little more or less than one answer. But error correction lives not in single answers, it lives in changes. If a check that was +1 last round is -1 this round, you mark a detection event. Plot those detection events across space and time, and you get a sparse constellation points that want to be joined in pairs by the most plausible paths errors could have taken. Finding those pairings efficiently is the decoding problem, and one of the workhorses is minimum weight, perfect matching. A graph algorithm that connects the dots along the cheapest routes, consistent with your noise model. Modern experiments even stream the decoding as the data arrive, allowing the graph to be matched on the fly while accounting for correlated error patterns. The geometry of the code turns that abstract graph into physics. In a distance D surface patch, the most damaging fault is a chain of single qubit errors that stretches from one boundary to the opposite boundary, because such a chain flips a logical operator. Crucially, as you grow the patch, the shortest such chain gets longer, so the probability that stray faults accidentally conspire to form it falls roughly exponentially, provided you're raw, physical error rates are below a certain threshold. That's the content of the threshold theorem in everyday language. And it's the logic behind scaling experiments that demonstrate the key signature: logical error rates going down as you move from smaller to larger codes. Boundaries themselves have character. In the surface code, we distinguish rough and smooth edges and strings of Pauli operators that implement logical X and logical Z run between specific boundary types. It's a simple, evocative picture. Logical operators are long fault lines drawn across the patch. Increasing code distance is stretching those faults farther apart, so random cracks, physical errors, struggle to connect them. That boundary story isn't decorative. It controls where excitations can begin and end, and it's what lets us visualize why one direction corresponds to logical X and the perpendicular direction to logical Z. Once you trust the patch, you can compute with it, but not by poking at single qubits. You compute by changing how patches touch. Lattice surgery is the gentlest and most useful move. You merge two neighboring code patches, so their shared boundary becomes a joint parity measurement, and later you split them again. By choosing whether a merge is rough or smooth, you decide which joint operator you measured, XX or ZZ, and with a short sequence of such merges and splits, you implement encoded entangling gates like the C0 without ever tearing the code. It's mechanics, not magic. Global logic built from local, nearest neighbor questions. There is a second layer to that choreography, one that lifts us from the tidy world of Clifford gates to full universality. Clifford operations inside a surface code are economical and fault-tolerant, but they are classically simulable. To escape that island, we inject magic states carefully prepared non-Clifford ancillus, and then consume and purify them by distillation until they are clean enough to drive T-gates at logical level. The idea is old and beautiful. Bravai and Kitaev showed that noisy non-Clifford resources can be concentrated into fewer, purer ones, and modern work has chiseled the overhead down with clever circuit identities and code choices, so the factories that produce those states can be smaller and faster. If you listen closely, you can hear how the engineering beats align with the mathematics. First, keep the physical error rates under the threshold, lower each gate's failure probability, improve measurement fidelity, reduce crosstalk. That buys you exponential suppression with code distance, as the threshold theorem promises. Second, keep the decoder close to the metal, so detection events are paired quickly and accurately, including correlations, for example from Y-type errors, that naive models miss. Third, prefer surgery over acrobatics. Merge and split patches to enact logic, so your hardware only needs short-range interactions. Each of those choices has moved from blackboard to lab. In 2023, for example, a superconducting qubit experiment showed the defining signature of scalable error correction. Logical performance improving as the code was made larger and run longer, a direct validation of the bigger can be better premise. You may wonder what becomes of the poetry when all this mechanism is in place. For me, it deepens. The picture of a code round ancillas waking, asking, listening. The decoder drawing quiet lines through a space-time lattice of little stutters. The logical state riding above the noise, like a melody above percussion, belongs to the same universe that gave us the double slit and entanglement. It is quantum mechanics rendered practical. The equations that once simply described how possibilities add now become the engineering grammar by which we prevent them from unraveling. And that is the wider moral. There is no rift between foundations and devices. Superposition and interference become algorithms, entanglement and decoherence become resources to be cultivated or tamed, thresholds and distances become the language of reliability. So, one more time through the cycle, prepare the ancillas, entangle them locally with their four neighbors, measure, reset, repeat. Watch syndromes turn into detection events. Let the decoder connect them by the gentlest paths. Apply tiny, surgical corrections that restore calm. Increase the patch size and feel the logical error rate fall away. When you need to compute, merge, and split patches with the care of a watchmaker, and when you need universality, feed in purified magic states like rare fuel. The whole sequence is unhurried, almost metronomic, and yet out of that patience comes something extraordinary. Information preserved not by isolation, but by relation. That, to me, is the right emotional cadence for fault-tolerant quantum computing. It is the music of many small, local acts, resolving into a global sentence the universe will not easily mishear. I like to pause after the hard mechanics and turn outward, because quantum theory isn't only an idea you keep safe under a refrigerator bell jar. It's a way of speaking to the world. The same grammar we've rehearsed: superposition, interference, entanglement, and the vigilant care of error correction now shows up as communication. You cannot silently eavesdrop on measurements that lean past classical limits, and clocks so steady they feel like tiny pieces of space-time domesticated in glass. When I talk about this publicly, I try to keep the cadence unhurried. Begin with the foundations, then show how those rules become tools. Take teleportation. Not Star Trek, but the sober, precise protocol from 1993. You and I first shared entanglement. I then perform a special joint measurement on my half of the pair and the state I want to send. That measurement yields 2 classical bits, which I must transmit to you in the ordinary way. When you apply unitary nudges conditioned on those bits, my original quantum state is reconstituted at your end, and the original is gone. No matter what moves, no signal outruns light. What travels is the quantum description, stitched back together only after the classical message arrives. It's a beautiful design because it wears the rules on its sleeve: entanglement for the shared resource, measurement as interaction, and classical communication as the sober chaperone that keeps causality intact. If you want the historical through line, Bell-type experiments earned the 2022 Nobel. Teleportation then turns that non-classical glue into a protocol. For a compact retrospective on the 1993 paper and the protocol's essentials, see these overviews. From there, it's a short step to quantum key distribution. The simple genius of BB84 is that security doesn't rely on arithmetic cleverness. It's baked into physics. Prepare single photons in one of 2 complementary bases. Any eavesdropper who tries to learn the key unavoidably disturbs the states, and the disturbance shows up as errors when we compare a fraction of the data. No perfect copying, no undetectable snooping. That's the no-cloning theorem at work, weaponized for privacy. The field has grown from a clean thought experiment into a practical discipline with protocols, security proofs, and hardware that moves beyond lab benches. For approachable technical surveys of BB84's logic and the modern state of QKD, start here. Link teleportation and QKD, and you glimpse a quantum network, entanglement distributed through fibers, free space links, and in headline-grabbing demonstrations, satellites, so that correlations survive across whole countries, and even, in proof of principle, between ground stations separated by thousands of kilometers. Those experiments are not magic tricks. They are confirmations that the world really does permit long baseline quantum coordination when you treat the photons gently enough. For a compact summary of teleportation's reach and the satellite milestone, see this overview. Sensing is where the quiet poetry of quantum mechanics becomes audible engineering. Consider LIGO, the Great Gravitational Wave Observatory. At its heart sits an interferometer so sensitive that quantum fluctuations of light-shot noise become a limiting whisper. One remedy is squeezing. You reduce the quantum uncertainty in the quadrature you care about and pay the price in the one you don't. Do it cleverly. Vary the squeezing across frequency, and the instrument hears fainter ripples in space-time than it otherwise could. That's not a metaphor. It's how the detectors improved their reach in recent runs, and it's a lovely example of quantum rules pressed into cosmic service. Atomic clocks take the same theme discipline of phase and turn it into time itself. The newest optical lattice clocks, built from strontium or ytterbium atoms, held in light's gentle grip, manage fractional uncertainties at the low 10 to the -18th level. In plain speech, if such a clock had been running since the birth of the universe, it would be off by less than a second. They can even resolve gravitational redshift across a millimeter of height, which is to say they can feel the curvature of space-time over a human hair's breadth. That is an almost absurd sentence, and yet it's the daily reality of modern timekeeping labs. The implications reach well beyond the elegance of the numbers. Transportable optical clocks are leaving their cloisters. Networks of them compare frequencies with 18-digit accuracy. Proposals for spaceborne clocks sketch a future in which timekeeping becomes a global quantum sensor for Earth science, navigation, and tests of fundamental physics. Metrology is preparing to redefine the very second around these devices. It is a quiet revolution, and it is entirely quantum. Line widths narrowed by isolation, phase shepherded by lasers, decoherence beaten back by design. Notice how the emotional register shifts as you move from foundations to practice. In the laboratory, we whisper to fragile states, protect the phase, ask gentle questions, keep entanglement pure. In the field, we do the same, just louder and with more plumbing. In QKD, we exploit the impossibility of undetected copying. In teleportation, we let measurement plus shared entanglement carry a state from here to there without outraging relativity. In sensing, we shape noise itself with squeezing, and use phase like a lever. In clocks, we let the atom's quantum rhythm define our heartbeat. You can trace each of those back to the stories we began with: the double slits interference, entanglement statistics, decoherence's insistence that the environment is always listening. The technology is simply the foundations made practical. If you prefer a single unifying image, take this. Quantum theory teaches us to treat information as physical and phase as precious. Everything else follows. Entanglement becomes a resource you can distribute, consume, distill. Interference becomes something you choreograph so wrong answers cancel and right ones sing. Error correction becomes the art of keeping phase relationships intact long enough to be useful. Squeezing becomes the choice to spend uncertainty where it hurts you least. Clocks become small, bright mirrors held up to space-time's flow. Where next? I'd like to lift the lens from bits and clocks to the deepest backdrop: quantum fields. The modern story says everything you've met, electrons, quarks, photons, is an excitation of a field that fills space. Even the Higgs, which gives mass to the fundamental particles, is a field with a non-zero value everywhere. In the next part, I'll walk quietly into that landscape. Why fields are the natural language, why particles are the ripples we name and count, and how the vacuum itself is not empty at all, but a restless ground, a sea whose subtle motion sets the stage for chemistry, stars, and us. For now, let the practical pictures settle. Keys shared by physics itself, ripples of space-time heard with quantum-shaped light, and time kept by atoms that have learned to hum almost perfectly in tune. I want to change lenses now, from particles to fields. The modern language says the world isn't built from little marbles. It's woven from continuous fields that fill all of space. Particles are what we call ripples, quantized excitations of those fields. A photon is an excitation of the electromagnetic field. An electron is a little packet of disturbance in the electron field. Once you accept that shift, everything becomes cleaner. Interactions are fields talking to fields, and the rules are written as a quantum field theory. Textbook plain versions of this are easiest to see in Quod at Demonstrand, summaries, and Britannica's entries on light as quantized fields and photons as field excitations. The collection of fields that best describes everyday matter is gathered under a single banner, the Standard Model. Quark fields and gluon fields knit protons and neutrons. Electron and neutrino fields sit in the lepton family. Gauge fields mediate forces. And one extra field, the Higgs field, quietly does something extraordinary. It gives mass to many elementary particles via the Brout-Englert-Higgs mechanism. The boson we discovered at CERN in 2012 was not the mass particle. It was a ripple in that Higgs field, a confirmation that the field really is everywhere. Only particles that couple to it feel the drag we call mass. That's why the 2012 Large Hadron Collider result was such a keystone. It wasn't just a new bump on a plot, it was evidence that the whole field-based story is true. If fields are the actors, the vacuum is the stage, and it's not empty. Even in the lowest energy state, quantum fields retain zero-point jitters. You can see this restless ground indirectly in exquisite spectroscopic details, such as the Lamb shift in hydrogen, a tiny displacement of energy levels caused by the electron's interaction with the fluctuating vacuum of the electromagnetic field. That wee nudge forced physics to grow up into quantum electrodynamics, one of the most accurate theories ever built. You can even feel the vacuum's hand as a force. Place two uncharged, closely spaced metal plates face to face. Some modes of the electromagnetic field are suppressed between them compared with outside. The imbalance in zero-point fluctuations nudges the plates together, the Casimir effect. In the late 1990s, Stephen Lamoureux's torsion pendulum experiment measured that attraction and found agreement with theory to within a few percent, and a large literature has refined and extended those tests ever since. The vacuum, in other words, is not nothing, it is structure. Antiparticles fit perfectly into this field picture. They are excitations of the same underlying fields, with opposite quantum numbers, opposite charge for instance. Bring a particle and its antiparticle together and the field relaxes. The excitations annihilate and energy rushes out, often as photons. You don't need metaphors to make this vivid. It falls straight out of the symmetries of the quantum fields themselves. The Higgs story is worth lingering over because it illustrates how fields can reshape the vacuum itself. Above a certain energy, the electroweak force is unified. As the universe cools, the Higgs field chooses a non-zero value everywhere, breaking the symmetry and endowing the carriers of the weak force and many matter fields with mass. The boson we found is just the smallest ripple on that sea, but the sea is the point. That one choice by the vacuum changes chemistry, stars, the possibility of us. But this lively vacuum brings a deep tension when we let it gravitate. Quantum field theory says every mode contributes a smidgen of zero-point energy. Add them up naively, and you predict an immense vacuum energy density. General relativity says vacuum energy acts like a cosmological constant that makes the universe swell faster. Observation, however, finds a value astonishingly small by comparison. Depending on how you count, the mismatch is tens to more than 100 orders of magnitude, often called the worst prediction in physics. We know the words to the song, but somewhere the harmony between quantum fields and gravity is missing. That is the cosmological constant problem, and it remains open. It's important to be precise here. Saying the vacuum isn't empty does not mean we can mine it like a battery. It means the lowest energy state of the fields contains correlations and fluctuations that leave fingerprints in careful experiments. Sometimes they appear as shifts in atomic levels, sometimes as forces, Casimir, sometimes as improved measurement strategies, squeeze states, and on cosmic scales perhaps as the faint pressure that accelerates the universe's expansion. The fact that these ideas all rhyme across such different arenas is one of the quiet pleasures of physics. What I find emotionally resonant about fields is how they unify opposites. Local and global, particle and wave, emptiness and energy, they stop being opponents and become perspectives. If I accelerate through the vacuum, what I call empty may acquire a temperature. If I change boundary conditions, new forces emerge. If I tune couplings, masses appear. A single grammar, many dialects. For the working physicist's view, reviews of vacuum fluctuation phenomena, how boundaries, media, or curvature coax the vacuum to show its hand, give a sober tour. None of this is an invitation to mysticism. It's an invitation to care about the details. Which field, which coupling, which symmetry, which boundary. The Standard Model's list of fields and charges is not arbitrary. It's the minimum kit that has survived every precision test we've devised so far, crowned by the Large Hadron Collider's observation of a scalar excitation with exactly the Higgs-like properties the model predicts. Each time we measure another decay, another spin parity correlation, we're checking that the ripple really is what the field story says it is. So picture the world tonight as a sea of fields, still and not still at once. The chair under you is a coherent arrangement of excitations. The light on the wall is a tidy parade of photon ripples. The space between them is alive with zero-point murmur. In the next part, I'll lean into one last layer of foundations and then pivot to the frontier, renormalization, the art of extracting finite, testable predictions from theories with infinite appetites, and why that same logic hints at where the Standard Model must end, pointing us toward new fields, new symmetries, and perhaps a gentler marriage between quantum theory and gravity. For now, let the field picture settle. Not marbles in a void, but music in a medium. Not empty space, but a stage with character and tone. When I first learned renormalization, I thought of it as tidying, a careful relabeling of what we mean by mass, charge, and field, so that the theory speaks only in measurable quantities. That's close to the truth. In practice, quantum field calculations can spit out divergences. Renormalization is the disciplined procedure that absorbs those infinities into a few physical parameters defined by experiment. So predictions become finite and precise. It isn't sweeping trouble under the rug, it's learning which parts of the calculation are bookkeeping and which parts are physics. But the deeper idea is that nature has scales. As you change the energy at which you interrogate a system, the effective strength of interactions shifts a phenomenon encoded by the renormalization group. Kenneth Wilson made that perspective concrete. Track how your theory's couplings flow as you zoom in or out, and you discover fixed points, universality, and the simple fact that different microscopes read different effective laws. This is why the same mathematics links particle physics with phase transitions in condensed matter. Scale is the common grammar. You can hear that grammar in the most practical way, the running of couplings. Electromagnetism's fine structure constant grows very slowly with energy. Quantum chromodynamics, the theory of quarks and gluons, does the opposite. Its coupling weakens at high energies, asymptotic freedom. That single sign in the beta function won the 2004 Nobel Prize because it explained why quarks act almost free at short distances, yet bind so stubbornly inside protons and neutrons. It also told experimentalists why high-energy scattering at hadron colliders looks partonic in just the way it does. Renormalization isn't only a conceptual victory, it's numerically ruthless. Consider the anomalous magnetic moment of the electron, G2. You can push the calculation through a forest of Feynman diagrams to 10 loops and compare with exquisitely careful measurements. The agreement is one of the great alignments of theory and experiment in science. That harmony is not an accident of clever tricks. Its renormalized quad are at demonstran dumb, doing exactly what it claims to do, predict reality in dozens of decimal places. If QCD's running makes you comfortable with scale, the Landau pole does the opposite. It reminds you that some theories may fail if extrapolated too naively. In quad at dem on stran dumb and simple scalar theories, the renormalized coupling drifts upward with energy and would diverge at a fantastically high scale, a pole in the flow. No one expects that to be physically accessible for electromagnetism, but the mathematical lesson is sobering. Quantum field theories can be effective rather than complete. They tell the truth over a range, not forever. That word effective isn't an insult, it's a strategy. Effective field theory says, write the most general description consistent with the symmetries you trust. Keep operators in order of importance. And accept that high-energy details you haven't resolved can be packaged into a few coefficients you measure. This is how we used Fermi's old four-fermion interaction long before we resolved the W and Z. It's how we relate low-energy data to high-energy possibilities across particle, nuclear, and condensed matter physics. All theories are effective might sound like a shrug. It isn't. It's a license to calculate responsibly. Once you start to think this way, renormalizability stops being a moral judgment and becomes a practical one. Renormalizable theories are those whose couplings don't proliferate as you raise the cutoff. They're economical descriptions that can be pushed to high energies. Non-renormalizable terms aren't forbidden. EFT tells you exactly how to include them, but their influence is suppressed by powers of the high scale. Between the two ideas running, couplings and power counting, you gain a map of what matters at the energies you can actually reach. There are two sides to that map. One is beautifully settled. QCD gets weak as you climb the energy ladder, so perturbation theory works in hard scattering. As you descend, the coupling grows and quarks confine. And you turn to lattice methods and effective descriptions. The other is unsettling. The Higgs sector refuses to tell us cleanly why the Higgs boson's mass sits where it does. Protecting a light scalar against heavy quantum corrections is the essence of the hierarchy problem, and the long conversation about naturalness, whether new symmetries, compositeness, or more subtle mechanisms keep the electroweak scale where we find it, and then there is gravity. In the same perturbative sense that makes quadrat demonstrandum and QCD so predictive, general relativity is non-renormalizable. At high energy, the quantum corrections proliferate and the ordinary recipe doesn't close. The mature response is again the EFT one. Treat GR as a low-energy effective theory. Compute the leading quantum corrections that are unambiguously predicted, and accept that some new description must take over nearer the Planck scale. There are many candidates for that deeper story. Some promise asymptotic safety, in which gravity's couplings find a fixed point. Others rewrite the degrees of freedom entirely. But whatever the UV completion is, it has to land on its feet as ordinary GR plus small quantum corrections at accessible energies. I find this comforting, not bleak. Renormalization taught us humility that is also power. Build theories that match the scale you can touch. Let symmetries and flows tell you what's universal. Be honest about cutoffs. It's why the standard model is so successful. It's a renormalizable core, wrapped in effective layers that we know how to handle, and also why we can be candid about its limits. The cosmological constant problem, neutrino masses, dark matter, the shape of the Higgs sector, all of these sit at the edge where our effective description is either whispering about the next scale or being oddly quiet. When I explain this in public, I keep the cadence slow. Start with the simple act of redefining parameters to speak only in measured quantities. Show how the renormalization group turns that act into a theory of scale. Let QCD's asymptotic freedom and the precision of quad erat dem on strand be the concrete anchors. Then allow the notion of effective to soften any urge for absolutism. It's the same arc I emphasized in that compact 22-minute interview. Gentle steps from foundations to frontiers. So here is the picture I carry to bed. A landscape layered by energy. At each height, the laws look slightly different, but the melody, the flow of couplings, the insistence on symmetry, the economy of renormalizable cores, dressed by small corrections, keeps recurring. Down where chemistry happens, the tune is familiar. Up at collider scales, the brass section takes over. QCD is bright and sharp. Closer to the Planck summit, the air thins and our instruments change. The score is unfinished. And that's all right. The renormalization group has already told us how to climb, one scale at a time, listening for the fixed points, trusting that whatever new theory waits in the thin air will, when we descend, hum the same themes we've been hearing all along. I want to fold everything we've built, superposition, fields, renormalization, into a single, clarifying picture. What quantum theory whispers about gravity, black holes, and the earliest moments of the universe. If fields are the actors and the vacuum is the stage, then black holes are the theater's most demanding acoustics. They don't merely sit there as dark spheres, they reshape the grammar of quantum fields around them. Stephen Hawking's calculation from the 1970s is still the cleanest doorway into this idea. Quantum fields near the event horizon are excited in such a way that an outside observer sees a very faint thermal glow. Hawking radiation and the black hole very slowly loses mass. The colder the hole, the bigger it is. The tiniest holes would evaporate most quickly. It's not a metaphor. It's a calculation that falls straight out of quantum field theory in curved space-time. Hawking's result ties back to something I hinted at earlier. The vacuum is not nothing. Even in the lowest energy state, quantum fields carry restless fluctuations. And what counts as empty depends on the path you take through space-time. If you accelerate through the vacuum, the mathematics predicts you'll perceive a warm haze, the Unruh effect. That statement sounds outrageous until you remember that particle content is observer-dependent in quantum field theory. Different motions slice time differently, and the vacuum defined by one motion need not be empty to another. The details are technical, but the melody is simple and beautiful. What you call nothing is in fact a structured state of fields, and your motion changes how that structure looks. Once you accept that, Hawking radiation feels less like a magic trick and more like the Unruh story told in the gravity dialect. Space and time are bent so severely around a black hole that the field modes on either side of the horizon are arranged in a very particular way. Far from the hole, you read that arrangement as a thin trickle of heat. The same logic leads to a sobering corollary. If the hole emits, it must also shrink. In principle, a black hole that can't feed will someday evaporate entirely. That conclusion raises a sharper question that has kept physics awake for decades. What happens to information? Hawking's first pass suggested the radiation was perfectly thermal featureless, and therefore that information about what fell in would be lost from our universe, a result that clashes with quantum theory's insistence that evolution is, at root, reversible. The argument matured into the information paradox, and for years the camps sparred. Either quantum theory blinks or general relativity's picture of horizons does. In the past few years, something much more interesting has happened. Using new tools, so-called quantum extremal surfaces, and the island prescription teams have calculated the entropy of Hawking radiation in toy models and found the famed Page curve. Radiation starts thermal, but correlations accumulate so that late in the process, information can, in principle, be recovered. It's not a full theory of evaporating astrophysical black holes, but it is a decisive hint that unitarity, the quantum rulebook, survives, and that we were missing part of the story of how space-time parcels information. For many of us, those papers changed the emotional register of the debate from stalemate to cautious optimism. I find it helpful to hold two images at once. One is Hawking's "Horizons teach quantum fields to hum a thermal note." The other is the newer page curve picture. Beneath that thermal note, subtle correlations are written into the radiation as the whole system evolves. Neither image lets you signal faster than light. Neither suggests that information conveniently jumps out of the hole. Instead, both insist on something quieter. If you ask the right global question about the entire field configuration, unitarity can be respected without violating the causal structure that relativity guards so jealously. That's an abstract sentence, but it captures a mood in the subject, an emerging sense that quantum theory and geometry are less enemies than reluctant collaborators. Step back a cosmic pace, and the same grammar appears in a warmer context, the birth of structure in our universe. According to the inflationary picture, a tiny, very early epoch of accelerated expansion stretched quantum fluctuations of the fields into macroscopic ripples, seed inhomogeneities that later gravity amplified into galaxies and clusters. We don't have to imagine this in the dark. We can see the imprints as slight temperature variations in the cosmic microwave background, mapped exquisitely by satellites. That faint stippling is quantum mechanics writ across the sky, frozen in light that left the primordial plasma when the universe was only a few 100,000 years old. The pattern statistics, their near-scale invariance, their acoustic peaks, are the most persuasive evidence that quantum fluctuations were indeed stretched to cosmic size. It's deeply satisfying that the same conceptual tools, vacuum fluctuations, fields, and the way geometry shapes what counts as a particle, explain both the hush around a black hole and the mottled face of the early sky. In Outreach, I sometimes say that quantum theory gives us permission to treat phase as precious. Gravity tells us how that precious phase is redshifted, stretched, and sometimes hidden behind horizons. Where the two meet, you get Hawking radiation at one extreme and the origin of cosmic structure at the other. If you'd like a compact, public-facing outline of how I frame this ladder from subatomic rules to cosmic signatures, I've sketched it in a recent 22-minute session. There's a human reason I keep the tone unhurried when I speak about this. The words can be heady: horizons, entropy, islands, inflation, but the underlying rhythm is gentle. Prepare a state, let it evolve, ask careful questions. In gravitational settings, careful means respecting horizons and the redshifts they impose. In cosmology, it means reading the sky's statistics as the fossil record of an early quantum sea. In both cases, we are reminded that measurement isn't peaking, it's interacting. That vacuum isn't nothing, it's a structured ground. And that information isn't a folk idea, it's part of the physical accounting a complete theory must keep. Where does this leave us? Not with answers yet, but with a path. The page curve calculations suggest that quantum mechanics remains whole in the presence of horizons. Hawking's radiation remains our cleanest hint that space-time has thermodynamic character. The microwave background remains a map of quantum whispers stretched to galactic size. Somewhere in the middle, where singularities should be tamed and geometry might emerge from entanglement, we'll need a new synthesis. Until then, the practical program is clear. Measure better, calculate honestly, and speak only in quantities that experiments and observations can touch. It's the philosophy that served us with Quaderat Dem on Strandum and QCD, and it remains our best guide under black skies and beside black holes. In the next part, I'll slow into the interpretations people argue about, how to read the wave function, what collapse might mean, how decoherence cleans the classical window, and then step back to the surface of the Earth, where quantum technologies make these abstractions audible in our instruments. Clocks that feel the lift of a millimeter, interferometers that hear the sigh of space-time, and networks that treat entanglement as a resource rather than a riddle. For now, keep two pictures side by side, a horizon, humming faintly, and a sky, faintly stippled, both of them the same song, played in different keys.